Hello, this is Concrete Path. Here is the lecture that's related to the problems. We have the problems related to that soil-water relationships that we have derived in the lecture 3. Let's take that number one. Let's take the number one problem. That's we have the we have the wide ratio of clay given. Wide ratio of clay sample is provided to you. Clay sample is given 0.73. Specific gravity of soil solids. Specific gravity of soil solids of that same material is that 2.7, and it's given that the whites are 92% saturated. Whites are 92% saturated. Okay, and we need to get the bulk unit weight, get the bulk unit weight, get the dry unit weight, get the water content, of that soil specimen, of that soil at this 92% saturation, at 92% saturation. At that same water content, at that same saturation degree of saturation, you need to calculate bulk unit weight, you need to calculate dry unit weight and water content of that same soil. If I say what is the bulk unit weight, what is the equation for that bulk unit weight? That is G plus SE 1 plus E times gamma W. And equation for gamma dry, that is G gamma W 1 plus E. Water content is weight of water by weight of solids. Now, can you see any of these data provided to you? What is the data provided to you? So our data is that we have a value of E given, we have the value of G also given, and we have value of S as 0.92 degree of saturation. So I think I can solve the first part of the problem can be solved now. Your bulk density, bulk unit weight can be solved as your G value was given to you. So your G value was 2.7. So I can write 2.7 plus saturation of 0.92, G plus SE, E value of 0.73 divided by 1 plus E, and this is you have to multiply with unit weight of that what you call as water, that is 9.81 kilonewton per meter cube. So finally your solution is equals to, your answer is this 19.118 kilonewton per meter cube. So second part of the problem is that G gamma W1 plus E. So G gamma W1 plus E, so 2.7 into gamma W. Your gamma W 9.81 divided by 1 plus E, that is equals to 15.318 kilonewton per meter cube. And this you also can solve that by the equation gamma bulk by 1 plus W. Gamma bulk by 1 plus W. And water content, what is the equation for water content? How can you get the water content? Because here the thing is that you are not given your data for the water, weight of water is not given, weight of the solid is also not given. So if for that you can write that SE equals to WG, and from that you would calculate that water content at that same saturation 0.92, so that would be equals to SE by WG. So SE, your saturation of 0.92 into your wide ratio at that same saturation 0.73 divided by the value of G, that is 2.7, and that water content is that's coming to be 0.248, or we can write 24.8% water content is there. Now, one more part of the problem we have to calculate, that we need to calculate what is the water content for complete. Calculate the water content. Calculate the water content for complete saturation of whites. Complete saturation. So we have this equation SE equals to WG, and I want that that complete saturation, that means S is equals to 1, and at that time your water content would be, let's write that W1, water content would be W1, but your value of E might change. Your value of E, we say we are going to assume that value remain constant. We're going to say assume E value assume it to be constant. If we assume that value of E is remaining constant, then we can write your value of water content at that time would be your 1 times 0.73, void ratio 0.73 divided by value of G, that is 2.7. And water content at that time, if you want that complete saturation of those pores, so at that time your water content is 27.03%. 27.03%. Okay, let's go for second problem. Let's take that second problem for that. Let's go for the second one. We have a sampler provided to you. A sampler is there. It's a that what you call as a small tool that's used to collect the material when we perform site investigation. So this is your sampler, and in that we can that fill it's filled with soil. Sampler filled with soil. So soil is filled. How much soil we have filled? So volume of the soil is 45 centimeter cube. So soil is filled inside that sampler. Okay. Now this soil, when you collect this soil from the field, now we are going to pour it in a graduated cylinder. There is one cylinder, graduated cylinder. Now we have a graduated cylinder. This soil is poured into graduated cylinder. Now it would occupy some volume. And let's say there was some water also placed inside that graduated cylinder. If there was some water and you are placing that soil now, so it would displace that water. So it says that it's going to displace water. It displaces water. How much water it displaces? 25 centimeter cube of water. This soil mass is going to displace 25 centimeter cube of that water. That means we need to get the value of porosity and void ratio for this data that is given to you. Okay. Sampler is there. You collected soil having volume of 45 centimeter cube, and this volume of 45 centimeter cube of soil you are placing in a cylinder which is having some water inside that, because you are placing some soil and soil is having some solids, and because of that your that's what you call as displacement of water is there, 25 centimeter cube. That means the solution would be in this way, that that volume of solids would be equals to 25 centimeter cube, because those solids would be the ones which are going to displace these are going to displace that water in the cylinder, displaces water in the cylinder. So that means your volume of solids would be actually 25 centimeter cube. And if I want to now write that what is the void ratio, that's actually volume of voids by volume of solids, where your volume of solids is 25 centimeter cube and your volume of voids would be now actually equals to volume of voids. We can write that is total volume of soil minus volume of solids, that is 45 centimeter cube minus 25, that's actually 20. So we can substitute here 20 centimeter cube. So this value of void ratio 0.8, void ratio of 0.8, and the porosity would be solved as volume of voids by total volume, that is 20 by 45, that's 0.444, and that we also can solve in this way. From the equation we have E by 1 plus E. So this was your second problem. Let's go for the third one. Let's take the third one. We have a Proctor compaction test. We have one Proctor compaction test. We'll be teaching that one also, Proctor compaction test. In that, what we are doing, soil, there is a soil which is having a bulk unit weight of 19 kilonewton per meter cube. Bulk unit weight of that soil is 19 kilonewton per meter cube at the rate of water content. At that time its water content was actually 15%. Now we need to find that what is the value of saturation if your G of the solids is actually 2.7. So we need to solve for the saturation at that time. If your solids are having G equals to 2.7. Okay, let's try to get the solution for this part. Let's try to get the solution for this part. We have equation S equals to WG. Our water content is given. Your value of G is also given. So to get the value of S, first you need to get the value of E. And we have given you that gamma bulk. If I write that gamma bulk equals to G plus SE 1 plus E gamma W, and we have the equation for that, what you call as SE equals to WG. But I would say you had two unknowns. Here we have two unknowns. Which of these are your two unknowns? Which of these are your two unknowns? One is the value of S, one is the value of E. So we have two unknowns from this relation. So that means we want to use the equation that's involving only one unknown. So let's talk about the dry unit weight. If I write that, what is the dry unit weight? Do you know the equation for dry unit weight? Is the equation for that dry unit weight equals to gamma bulk by 1 plus W, and the dry unit weight is actually equals to G gamma W 1 plus E. If I write it in this way, now if we see that we have only one unknown, that's your wide ratio of E. Once I get the wide ratio of E, I can get the that value of S. Do you see that? So if I substitute those values in the equation, if I write that, that means that 19 kilonewton per meter cube is your gamma bulk divided by 1 plus water content, 1 plus 0.15. That should be equals to 2.7 gamma W 9.81 kilonewton per meter cube divided by 1 plus E. So your value of E can be solved as it comes to be equals to 0.603. So your wide ratio we got. So at that same wide ratio we can calculate what is the saturation. So saturation would be calculated as WG by E. So let's substitute those values that are given to us. Your water content is there. So we can substitute water content of 0.15. Your value of G is 2.7 divided by that wide ratio of 0.603. So your saturation is actually how much? 0.6715, or we can write 67.15%. Okay, that means out of the total volume of voids, out of the total pores, your 67.15% of the pores are filled with water. We can say that. Let's go for the fourth case of the problem. In this problem itself we have one more part of the problem. Yeah, in this problem we have one more part to solve. Part B we have to calculate. Part B of the problem is that you need to get additional moisture content. Get the additional moisture content for saturating the soil specimen. So this is saying that this means that for value of S is equals to 1, get the value of water content as water content W1, and from that tell me the extra water you need to add. What is the extra water content you need to add? What's the extra water content we need to add? So for that, let's say that initially you got at saturation of 67.15, how much water content we need? 0.15. That means 15% of water content we need for saturating 67.15% of the pores. And for this case, that if the saturation is 100%, how much water content we have to add? So we can assume that your wide ratio remains same. Let's assume that your wide ratio remains same. Assume that E remains same, then we can write SE equals to WG. So your W1 would be equals to actual value of SE by G. So your S is actually here 1, and your wide ratio we said that is going to remain constant, 0.603 divided by value of G, that is 2.7. So your second water content would be actually that's almost equals to 22.33%. So initially it was that 15% of water content was there at the rate of saturation equals to 67.15%. Now I would say what is the extra water content we have to add? So the extra water content is actually that W1 minus initial value of W. So that's 22.23 minus 15. So this much amount of percentage of the water content we had to add 7.33% of the, I would say 7.23 to be more clear, that 7.23% of the extra water content we have to add, such that your saturation changes from 67.15 to 100%. Let's go for the problem 5. Let's go for the problem 5. Problem number 5. So we have a specimen, we have a mold. Let's say this is our mold of steel. This is your mold of steel of dimensions that this is your 50 millimeter diameter. Dia is 50 millimeters and height is 100 millimeters. So this is your mold, and in that we want to fill the soil. So we want to fill the soil. So soil we have to fill, and the soil here, that's actually dry soil. Soil is dry soil. Soil is actually dry soil. So now the problem is that we have a compacted cylindrical specimen made from dry soil. Compacted cylindrical specimen of dry soil. That's because of this one, because of the specimen we have. Now the specification for the soil is that, what is the specifications for the soil? What should our dry soil look like? It should have percentage of air voids. Percentage of air void is equals to 20. 20% of the air voids is there, and we have also one more thing, that water content should be equals to 15%. Water content should be 15%, and now we need to calculate, get the bulk weight of the soil. So get the unit weight of the soil. That is we can say gamma bulk unit weight corresponding to bulk condition. So get the bulk unit weight of the soil. This is one of the problem, and we need to say what should be the water required for preparation of the soil. How much water you need to add? Water required for preparation of soil specimen. Required for preparation of soil specimen. And your G value for the soil solid is 2.69. So what is the actual scenario? That I want a specimen. I want to make a mold. I want to make a specimen of dimensions. This is our clay specimen, I would say. This is our soil specimen. This is only clay. This is your soil specimen, soil. So its dimensions are already known to us. That means the volume of the soil, I already know how much volume of the soil I have to make. But I have to make the specimen from the dry soil. But at the rate of water content equals to 15%, and percentage air void is 20%. That means I have to make what you call as a mix in a way that the mix should have water content of 15%, and it should have percentage of air voids as 20. So at that time I would say how much water I have to add such that your water content is 15%. That means the weight of water by weight of solids is 0.15. So if I am adding that weight of solids by some amount, and I have to add weight of water as 0.15 times of that weight of solids, such that your final volume of the total soil is this much. Okay, this is our total volume of the soil. And I know one more thing, that this was your initial value of dry soil. Now there would be now bulk unit weight as per the requirements, as per the specifications. Our that soil specimen would be in the bulk condition. So can you get the solution? Can you get the solution now? If I talk about what is this percentage air voids, what is the equation for that percentage air voids? So it says that how much is the volume of air with respect to the total volume of the soil specimen, and that's given to you as 20%. That means 0.2. So volume of air is actually 0.2 times total volume of the specimen. Can I get the total volume of the specimen? What is the total volume of the specimen? Can you tell me what is the total volume of the specimen based on the dimensions we have? So I would say volume of the specimen is actually your pi by 4 d pi r square h, that's pi by 4 d square pi by 4 d square into h, and the units are in millimeter power 3, millimeter power 3, millimeter power 3. So this is your volume of the specimen, and out of that 0.2% is contributed by air. That means all the other data, that is only because of volume of water and volume of what you call as solids. So if we make a phase diagram, I would say we have solids, we have water, we have air, and the volume of air, if there was total volume of V, volume of air is 0.2 V. That means the left part of the volume, that is 0.8 V. So I would say 0.8 V. That means 0.8 times V is actually volume of water plus volume of solids. And from this we can get the we need to calculate water required. That means what is the weight of the water to be added? What is the weight of the water to be added? That means the water required for these set of conditions. So can we calculate what should be the value of that water to be required? Can you calculate that? So I would say this part of the problem is, or this is not of now, this is of no use now, because I have calculated what is the now final volume. That's 0.8 of the total volume is now equals to volume of water plus volume of solids. Let's remove this part. Now I have the value of G. I have the value of what you call as W equals to 15%. Water content is also given to you. So if I say what is the equation for water content? Water content is actually 0.15. That is weight of water by weight of solids. So actually the data is given to you in terms of weight, and we need to calculate also water in terms of weight. So we have to replace these volumes, volume of water and volume of solids, in terms of weight of water and weight of solids. So let's convert them. In terms of weight. So I would write 0.8 times volume equals to, what is the volume of water? Is that weight of water by gamma W? Can we write that? Plus weight of the volume of the solid is actually weight of solids by G times gamma W. So this is the equation we have. And we also know one more equation, that water content is 0.15. So if I say what is the weight of water actually is, that is 0.15 times weight of solids, based on this equation. That weight of water is actually 0.15 times weight of solids. So let's substitute that value here. So that means I'm going to write that 1 by gamma W outside, and I am going to write that 0.15 times weight of solids plus weight of solids by G times gamma W. That is outside. I have kept the gamma W outside. So you have this equation now. And we can substitute the value of V also, 0.8 into volume, pi by 4, 50 square, 100. This is 100 actually. This should be 100. Yeah, this was 100. So finally millimeter cube. And we can substitute the value of gamma also now. Gamma is actually 9.81 kilonewton per meter cube. So we got this equation now. And from this we can solve for the value of Ws. Let's substitute the value of G also now. Let's substitute the value of G. The value of G is 2.69. If I simplify it further, I can solve for the weight of solids. That's actually equals to 0.8 into pi by 4. You can solve the value directly. You can calculate it directly. That's in millimeter cube, and into multiple of that 9.81. Kilonewton per meter cube, and in the denominator you are left with that 0.15 plus 1 by 2.69. So you can solve it such that your weight of solid is finally coming out to be some kilonewtons. That is some 2.952 newtons. So this is the weight of solids you are getting finally. This much amount of newtons is the weight of solids required for that sample of total volume of V. Okay. So we got the total volume of weight of solids. Yeah, we got the total weight of solids. Now we need to calculate actually what should be the water required for preparation of soil specimen. Water required. So water required is the weight of water is equals to 0.15 times weight of solids, newtons. So this much amount of newtons of water we have to apply. We have to add this much amount of water. That is, let me check that value in terms of those newtons. That is 0.15 into 2.952. That is 0.4428 newtons. This much amount of newtons. And if I want to calculate in terms of kgs, I would say this is your weight, and that is equals to some mass of water into that 9.81. That's gram per. That would write here in terms of meter per second square. So I would write what is the value of mass of water to be added. Mass of water to be added, that would be 0.4428 divided by 9.81. So this much amount of kgs, 0.0451 kgs, and that means 451 grams. That means how much? You have to multiply 1000 with that. 1000. That is 45.1376. 45.1. So this much amount of grams we have to apply. 45.1 grams of water we have to add. So this much amount of water I have to add for the sample, for that dry sample, such that your final specimen is having some volume of V and having some weight of solids and some weight of water. Okay. So this part of the problem is over, and we need to calculate also that what is the gamma of the soil. That is the bulk unit weight. What is the bulk unit weight of that soil? Can you calculate that? You had this specimen. You are applying that water. You are applying that solid also. So I would say your gamma bulk would be weight of water plus weight of solids divided by total volume V. So weight of solids we calculated as weight of water was actually 0.4428 newtons, plus weight of solids is 2.952 newtons divided by total volume of pi by 4 50 square into 100 millimeter power 3. So based on these calculations, let me go for the solution. That's 0.4428 plus 2.952 divided by 0.25 into divided by pi by 4 d square into 100 into 100. So I got that value. I have to multiply that because I want to convert it in terms of kilonewton per meter cube. So I had to multiply at the top. I had to multiply at the top. At the top, I had to multiply 10 to the power minus 3 such that it is going to become that kilonewtons, such that it becomes kilonewtons. And at the bottom, I have to multiply that 10 to the power minus 9 such that it becomes meter cube. So finally, I have to multiply 10 to the power 6 overall value. I have to multiply to the overall solution answer, that's with the multiple of 10 to the power 6. So that's 17.2896. So finally, gamma bulk unit weight of that soil specimen formed is equals to 17.2896 kilonewton per meter cube. And from that, I can also get the what you call as dry unit weight. That's actually gamma bulk by 1 plus W. That's actually 17.2896 divided by 1 plus 0.15. So that's also we can solve 1.15. That's 15.03 kilonewton per meter cube. Okay, let's go for one more problem. This is your beautiful one. Let's write it as number 7. So we are going to excavate soil. Let's say there is a pit. There's a ground level. I'm going to excavate soil from here. I'm going to excavate soil from this pit. We call it as borrow pit. From this pit, I am going to excavate soil. Okay. So here the soil here is having what you call as density of 1.75 gram per cc. That's the bulk unit weight, we can say, because it's in the field condition. So this is bulk unit weight of 1.75 gram per cc. It's given in terms of density. And after that, water content is also given to you. Water content at this borrow pit, that is 12%. Water content is 12%. Okay. Now we want to we want to transport this soil, excavated soil, to some location such that somewhere I want to compact this soil at a particular location that we call as embankment, or we can say that is fill. So there is some fill, or we can write that as embankment. I want to transport this soil now. There is transportation of this soil to some other location. At that location, I want to fill that soil. So at that, the condition is that I want specification of the soil here. Compacted soil should be there. The soil here should be compacted. Let's say I want it for the road construction, or any other construction. Let's say that I want it compacted. So the specifications are given to you that here the gamma we need, the density we need here, that should be density here, that is dry density. It is dry density at the embankment, that should be equals to 1.65 gram per cc, and water content needed here is 18%. Water content also needed here is 18%. Okay, so it's now saying that for 100 for 1000, yeah, for 1000 meter cube of soil in the fill, for 100 meter cube of soil in the fill, get the quantity get the quantity of soil excavated from the pit, in meter cubes. So quantity means that volume. And second part of the problem is that how much water has to be added. How much water has to be added? And third one is there, what is the void ratio of soil in backfill, in the fill, I would say, in the fill and in the borrow pit, So first part, that means I want 1000 meter cube of soil in the fill. So I need how much amount of soil in the fill? I need 1000 meter cube of soil in the fill. So this fill needs that I want to design something such that I need total volume of soil equals to 1000 meter cube at the fill. So for having this soil amount of 1000 meter cube, how much soil I have to excavate from this borrow pit? How can you calculate that? So here we have different density. Here we have some density, that is bulk density, and different water content. At this location, we have different water content and different dry density. So one more data is given to you, that specific gravity of the soil solidus is, this is of the solidus, that is 2.7. Now how can you solve it? So for these kinds of problems, that's excavation and transportation kind of problems, so you can write that for excavation and transportation problems, we have that concept that total weight of solids is going to remain constant. This is constant, it is not going to change, and total volume of solid is also going to remain constant. So we have to calculate those. We have to relate the two conditions. We have to relate the two conditions of borrow pit and fill by that one, that because weight of the solid is the same, so we are going to relate both the two sites by this weight of solids. And similarly, either we can relate it by weight of solids, or we can relate it by volume of solids. So by these two parameters, we can relate the two sites. One is your borrow pit. Next one is your that fill site, where you want to fill that material. Okay. So this is our concept, that weight of solid is remaining constant and volume of solid is remaining constant. And for that, we have equation that we derived. We have derivations of those. We write that total. Yeah, we write total weight of the soil. Total weight of the soil is actually weight of solids plus into 1 plus water content. This was one of the equations that we derived. This was the first equation that we derived. And one more equation was that this was the second equation that we derived. Volume of soil is actually volume of solids into 1 plus void ratio. This is the equation. With these two equations, we are going to use in these concepts, in this concept of excavation and transportation. Now, I would say as per the data, as per the data, as per the data, I can solve either in terms of water content, or I can solve it in terms of a void ratio. So I also need to calculate void ratio. I also need to calculate void ratio. Let me go by the concept of void ratio. Let me go by the concept of void ratio. So so the solution would begin in such a way that let's go for the solution. Let's go for the solution. So solution would be, I would say, your volume of solids remains constant. Remains constant. It's going to remain constant. And I have the equation that let's talk about the first case. Let's talk about the first case. Let me talk about the first case. That's about the, let me check the condition. Let me take the first condition, that's about the borrow pit. Borrow pit. Let's talk about the borrow pit. Let's talk about the borrow pit first. Okay. So I would say, what is the equation for your gamma bulk? We can write in terms of rho bulk also, density bulk density. So what is the equation for gamma bulk? What is the equation for gamma bulk? We are talking about, let's say this is borrow pit. We are calculating for borrow pit. We are going to use these data as borrow pit. I would say your gamma bulk is actually rho. Yeah, we are saying rho bulk. So that's that's rho dry into 1 plus E borrow pit, EB, we can write EB. So this is the equation. Actually, it should be gamma bulk is equals to gamma dry 1 plus E. Do you know that equation? We have derived this equation. So based on that, I can get the value of what you call as, I can get the value of void ratio. I can get the value of void ratio. Let me try to get the solution. I would say your bulk weight is given to you in terms of density, that is 1.75 gram per cc. Okay, let's remove those units. I would say this is your 1.75, and your dry density should be, what is the equation for dry density? Is that G gamma W 1 plus E? So here we can write G gamma W 1 plus E. Your gamma W had to be replaced by that rho W. And what is the density of water? Is that 1 gram per cc? So we can write here rho W is 1. So so this part would be G gamma W 1 plus E into 1 plus E times bulk, 1 plus E bulk. So here we can write G rho, then finally substitute those values. Yeah, this is not the equation. The equation is that rho bulk is gamma bulk is actually gamma dry into 1 plus W into 1 plus W. This is the equation actually. This is the actual equation. Gamma bulk is gamma dry 1 plus water content. And I have the equation for gamma dry. That's actually let's say that we have the equation that gamma bulk is gamma dry, and gamma dry is G gamma W 1 plus E, and we can write it here E borrow pit, and into 1 plus W. And I know the data. Which of the data I know? Can you tell me which of the data I know? So I know G value also. I know rho bulk also. I know water content also. So I can get the value of E bulk. I can get the value of E borrow pit. So let's substitute those values. Here. I would say you had this density 1.75, and you had this G value of 2.7. Your solid's value of G is going to remain constant. That is the absolute specific gravity G, 2.7. 2.7 into your value of gamma W in terms of density, so that's 1 gram per cc, divided by 1 plus E borrow pit into 1 plus water content. Water content is that 12%, so 0.12. So that means your void ratio for the borrow pit would be, void ratio in the borrow pit is actually how much? 0.728. So we got one of the part of the problem, that was to calculate the void ratio in the borrow pit. So this part we got, and this would be very useful in calculating that volume of soil to be excavated. So once I got this part, and I need to say what should be the, how much volume of soil, how much volume of soil for 100 meter cube of soil in fill, for 100 meter cube of soil in fill, how much soil I have to excavate from borrow pit. And for that I have the equation that volume of soil required is actually volume of solids into 1 plus E. If I talk about what is the volume of borrow pit, how I have to excavate, I would say that is actually volume of solids into 1 plus E borrow pit. So I got the value of E borrow pit, but I don't know the value of V solids. I don't know the value of E solids. So to get the value of V solids, I have to use the one more equation that volume of fill, volume of fill, volume of total soil in the fill should be equals to volume of solids into 1 plus E times fill. So I need to calculate now what is the void ratio in the fill for your volume of fill equals to 1000 meter cube. From that I can get the volume of solids. Then I substitute the volume of solids here. Then I can get the volume of that borrow pit. So this is the procedure we have to use. This is the procedure we have to use. So let me use it. Let me keep it somewhere here. Let's say this is our procedure to get to be. This is our procedure that is going to be used. So this is the procedure that we have to use. Now, so I would say let's calculate the void ratio in the. Let's calculate the void ratio for your fill. Let's calculate the void ratio for your fill. Void ratio calculations for fill. So let's calculate E fill. For that, I have the equation that gamma dry is equals to G gamma W1 plus E. If I write that this is related to the fill, so I would write G gamma W1 plus gamma dry is equals to G gamma W1 plus E, and this is your related to your fill material. And the density here is it's given to you. Your dry density is given to you 1.65 gram per cc. So we can use the values 1.65. So we can use those values in terms of density. So I would write 1.65 gram per cc should be equals to G value of 2.7 into unit weight of gamma. That gamma W should be in terms of rho W. Rho W is equals to 1 gram per cc. So we can write 1 gram per centimeter cube divided by 1 plus E. And this E is related to a fill, so I can write 1 plus EF. So your EF can be solved as your void ratio for the fill material is 0.6364. 0.6364. 0.6364. So I got the void ratio. Now if I got the void ratio, so now I am calculating that equation. Let's talk about that fill, same fill, that void ratio, that volume of soil is actually volume of solids into 1 plus E fill. If I calculate for the fill how much solids I have to use, if I calculate for solids for fill how much solids I have to use, I would be writing that volume of total volume of soil should be volume of solids into 1 plus EF. So this part is I know that 1 plus 0.6364. Okay. Now what is the volume of solids and for how much volume of soil? So this was your given data that for 1000 meter cube of soil in fill, how much I can get the volume of solids. For 1000 meter cube of soil in the fill, how much that volume of solids we had to use. So that we would say volume of solids is coming out to be 611.1111 meter cube. So this is the volume of solids we have to use. But the question is not saying get the volume of solids. It's saying get the volume of soil, but where? That should be excavated from the borrow pit. From the borrow pit, I had to calculate now what is the volume of borrow pit for that same amount of solids. For the same amount of solids, how much soil we have to excavate from the fill. So for that, I would say corresponding to this value of Vs, how much volume of solids is required. How much volume of soil is required? So V required is actually volume of borrow pit actually required is equals to volume of solids into 1 plus E borrow pit. This is the equation. So I have the equation that so volume of soil from the borrow pit I have to excavate, that should be 611.1111 meter cube times 1 plus E borrow pit 0.728. So this is the final equation. This is the final solution that how much volume we have to excavate from the borrow pit. That's coming to be 1056 meter cube. So that means for 1000 meter cube of soil to be placed at the fill, I need 1000 meter cube of soil at the fill, but I had to excavate how much? 1056 from what you call as borrow pit. So that means there is some compaction. Because of some compaction is there, because there's some compaction, so more soil we needed to excavate. That's 56 meter cube more. 56 meter cube more. Okay. Okay, do you got that? First part. And third part we also have calculated. First part we have calculated, third part we also calculated. And we need to calculate now what should be the water that we have to add. Water to be added. So initially the initial water content of the field condition was 12%. 12% was the initial water content. And here we have water content of 18%. We have water content of 18%. So how much extra water content we have to provide? How much water content we have to provide that's extra? So we have the equation that water content is actually a weight of water by weight of solids. If the weight of solid is fixed in both the sides, it's fixed in both the sides, borrow pit and what you call as fill. If the weight of solid is fixed, that means your water content is changing by only that weight of water. So I would say how much water we have to add, that would be actually water content 2 minus water content 1, water content 2 minus water content 1 times weight of solids. So let's see how. I would say in the initial case, your weight of water content was initially how much? If I talk about that borrow pit, 12% was your water content, 12%. So that's actually weight of water content divided by weight of solids. For this is related to borrow pit. And if I say what is the water content in the fill site, what is the water content in the fill site? That is 18%. That is 18%. 0.18. That is some weight of water divided by weight of solids. Now I would say for this was related to fill, and first one is related to borrow pit. Okay, I would write here, this is the water content at the borrow pit, this is the water content at the fill site, and this is the water content weight of water at the borrow pit, this is the weight of water at the fill site. But your weight of solid is fixed. We can write here weight of solid is fixed. Weight of solid is fixed because your volume of solid is also fixed, so weight of solids is also fixed. They are not going to change because your solids are incompressible. Okay, now from that I would say how much extra water we have to provide, how much water to be provided, water to be added, how much water we have to add. That is actually weight of water in the fill site minus weight of water in the borrow pit site. Can we say that? That is the weight of water to be added? Difference of the two. So I would say that is 0.18 minus 0.12 times weight of solids. Now we need to calculate first what is the weight of solids. What's the weight of solids? Can we calculate weight of solids? If I know volume of solids, can I calculate weight of solids? Weight of solids can be calculated as G gamma W into volume of solids. So G of the material is 2.7 given to you, 2.7, and you can use the gamma W as 9.81 kilonewton per meter cube, and your volume of solid is 611.1111 meter cube. So your weight of solid is that's we have to use how much weight of solids? That is 971.2. I think how much that is weight of solids? We can solve that. That is 2.7 into 9.81 into 611.1111. So this value is 16186.9.4997 kilonewton. This much amount of weight of solid is there. So I would say what is the water content? What is the total weight of water we have to add? That is 0.18 minus 0.12. So finally I would write water added is equals to 0.18 minus 0.12 times this value of 16186.497 kilonewton. So this value is coming to be equals to 971.2 kilonewton. So this much amount of water we have to add, such that your specifications of those borrow that fill is achieved. Okay, so this was a very beautiful problem we can have. Okay, that's related to excavation and transportation. Let's take the problem 8. Let's take the problem number 8. Let's go for the problem number 8. Problem number 8, similar to that of a previous one. Similar to that of a previous one, we have borrow pit, we have a borrow pit, we have a borrow pit, and earth we have to remove. Earth is what you call as excavated from there. Earth excavated for building the for building embankment, for building an embankment. So we have to make design some embankment. For that we need this soil, we need this earth material, and the dimensions for the embankment is that we have top width of 2 meters and the side slope is 1:1, and height of the what you call as embankment is 6 meters. So I would say there is some 6 meters height, so such that your side slope is also 1:1. So I would say this part is actually 6 meters. For if the side slope is 1, so I would say this would be also 6, and from the other side also we can have same side slope. So the total length at the bottom would be 6 plus 6 plus 2, that is 14 meters. So we have this area cross section of that embankment. This is the area cross section of the embankment, that's semi-parallel sides into that height of 6. So this is the area of the cross section of that embankment. Okay, now your borrow pit specification is that the borrow pit has that gamma bulk of 18 kilonewton per meter cube, and water content is there 8% natural water content. So this is the natural condition we have related to that soil. Okay, and in the embankment, what is the specifications we need to have? For the embankment, we need to have dry unit weight 20 kilonewton per meter cube, dry unit weight. For the water content, that should be 10%, and your specific gravity for the solids is 2.7. Okay, so let's go for the first part of the problem. First part of the problem is that to calculate the quantity of earth excavated quantity of earth excavated from borrow pit. Okay, quantity of earth excavated from borrow pit for 1 meter length of embankment. For 1 meter length of embankment. So what should be that volume of borrow pit required for 1 meter length of embankment? So if we have this embankment, and if I take that 1 meter of that, let's take that 1 meter of that. I would say there is some 1 meter of that. Let's say this is our 1 meter of that embankment. This is 1 meter. Length equals to 1 meters. Can you get the volume? What is the total volume of soil required? Can you get what is the total volume of soil required for these dimensions? So total volume of the soil required, in the embankment. This is your embankment. What is the total volume of soil required for the embankment? That is actually some volume of solids into 1 plus E embankment, but your value of soil is actually how much? Can you calculate the area, that volume? So this is 1/2 semi-parallel sides into that depth of 6 into that length of 1 meter. So it becomes finally meter cube. Some value of meter cube, that is 16, 8 6s are 48 meter cube of volume we had to use. So I would say for 48 meter cube of soil in embankment, how much soil we have to excavate from borrow pit? This is the problem. Can you calculate that based on the previous way, based on the way that we solved previous problem? 48 meter cube. So if I write that equation again, that your gamma bulk, what you call as gamma bulk in the borrow pit condition. Let's say this is our borrow pit condition. Gamma bulk is actually gamma dry divided by 1 plus, yeah, gamma dry into 1 plus W. This is the equation for that. Gamma bulk equals to gamma dry into 1 plus water content. And let's substitute these values. This is your 18. And what is the value of gamma dry? That is equals to G gamma W 1 plus E and 1 plus W. And from that I can get the void ratio. I can get the void ratio for borrow pit. So that we can say this is your G value of 2.7, value of gamma W is 9.81 divided by 1 plus E bulk into 1 plus water content 0.08. So from that you can get the void ratio for your borrow pit. That's coming out to be 0.5892. This is your void ratio required, void ratio of that material in the natural condition, in the borrow pit condition. Now we have to get the volume of borrow pit, and for that we have the equation of that volume of solids into 1 plus E borrow pit. So we got the value of E borrow pit. Now we need to get the value of volume of that solids. For that we have to come back to what you call as to the embankment side. We have to come back to the embankment side, and from the side we need to calculate now what should be the volume of solids required. So this is the volume of solids. This means this is the volume of solids required for how much volume of soil? For volume of soil equals to 48 meter cube in the embankment. How much volume of solids I need? So that can be solved as 48 meter cube is equals to volume of solids into 1 plus E embankment. Can we write that? Total volume of 48 is there. It is the total volume of soil for your embankment, and that should be equals to volume of solids into 1 plus EE. So we need to calculate EE. So your EE can be solved from the data this is given to you. So gamma dry, this is related to embankment. We can write G gamma W 1 plus E. From that we can write EE. So we can solve EE. So EE can be solved here. Let's substitute the values to get the value of EE. So we can write here 20 kilonewton per meter cube is equals to 2.7 into 9.81 divided by 1 plus EE. That EE comes out to be 0.3245. So I got the value of EE. Can you get the value of volume of solids? 0.3245. So volume of solids finally comes to be, volume of solid is coming to be 36.2401 meter cube. So for this much volume of solids, how much volume of soil I need to excavate? So for that I would write here equation that 36.2401 meter cube of volume of solids into 1 plus E bulk, E borrow pit, that is 0.5892. So that comes to be volume of soil of the borrow pit to be excavated is equals to 57.5935 meter cube. So this is the volume of soil we need to excavate from the borrow pit. Now let's come to the second part of the problem. Second part of the problem is there. Second part of the problem is says that calculate how much number of tracks we have to how much number of tracks we need, how much number of tracks we have to load, that's loading, how much number of trucks we have to load such that, yeah, for 1 meter embankment, that means for 48 meter cube of volume in the embankment. So for that 1 meter embankment, how much number of trucks we have to load such that one truck has the capacity, one truck capacity is given. So one truck can take how much soil? Truck capacity is equals to, so one truck capacity is 80 kilonewton per trip. This is the capacity for your one truck. So one truck capacity is 80 kilonewton per trip. So we need to say how much. Uh, so so for this data of 1 meter embankment, I need to say how much weight of the soil I have to what you call as transport. What is the weight of soil I had to transport? Because your capacity of the one truck is that it is capacity is 80 kilonewton, 80 kilonewton of that soil per trip. So I would say what is the total weight of soil in kilonewtons. After that I can say how much number of trucks we need. So I would say your weight of soil can be solved for 1 meter embankment. That means for 1 meter embankment, that is actually equals to 48 meter cube volume of the soil in the embankment. For that, how much weight of soil we should have? How much weight of soil? So that weight of soil is actually weight of solids into 1 plus water content in the embankment site. Can we write here? Can we write that in this way? Can we write that in this way? Can we write that in this way? I think we can write that in this way. And one more thing is there. We would say how can you get the weight of solids? I know what is the water content at the embankment. I know what's the water content at the embankment. Water content at the embankment is 10%. Okay, that I know. Okay, 10%. This part I know. That means this is 1 plus 0.1. This is 10%. But how can you get the weight of solids? What is the equation for weight of solids? Is this the equation for weight of solids? G gamma W Vs, and Vs I already know for 1 meter cube of for 1 meter embankment. How much weight of solids we have to calculate? We have to take. This was the volume of solids we have to take. 36.2401. 36.2401. So let's substitute those values here. I would write 36.2401 meter cube of volume of solids into that specific gravity of 2.7 into gamma water of 9.81. This was your kilonewton per meter cube. So this is the total weight of solids into that 1 plus water content, 1 plus 0.1. So from that, your weight of soil that we need to have, that should be equals to 1036.6828 kilonewton. This much amount of soil we have to transport to what you call as embankment. And it says that our capacity of one truck is 80 kilonewton. So what is the number of trips we need to have? So number of trips can be solved as n number of trips of that particular truck. So that's actually total soil 1036.6828 kilonewton divided by 80 kilonewton. That is almost coming out to be equals to 13 trips. We can have 13 trips. And the third part of the problem is that now we need to calculate porosity and saturation, degree of saturation on embankment. Third part of the problem is there. Porosity, calculate porosity and degree of saturation in the embankment. So for that particular soil in the embankment, what is the porosity and saturation? Porosity and saturation. So that's actually porosity is a volume of voids by volume of total volume, and your what you call as saturation is volume of water by volume of solids, volume of water, volume of voids. Okay, but we are not going in this way. We can use the equations that we have in terms of gamma. So we have the equation that gamma dry equals to G gamma W1 plus E. And we also have one more equation, that is standard equation, SE equals to WG. Now from that I might get the values. I might get the value of S. If I calculate for the embankment, EE, W embankment, and G is fixed, so I can get the saturation for your embankment. That's actually S equals to WEG by EE. So we know already those values of WE and EE. Let me try that. Let me check those values. Water content in the embankment, 10%. water content in the embankment is 10% and void ratio 0.3245. So 0.1 is the water content, G is 2.7, and void ratio 0.3245. Your saturation in the embankment is actually how much? 83.2%. And once I know the value of E, can you get the value of porosity? Once you know the value of E, can you get the value of porosity? So your porosity can be solved as E by 1 plus E, E by 1 plus E, E by 1 plus E. That is actually volume of voids by total volume. Now, if we say that we have this three-phase diagram, that we have solids, water, and air. If I take that volume of solids as 1 meter cube, that volume of solids is equals to 1 meter cube. That means your volume of voids is actually only E times E meter cube. Your volume of voids would be actually actually this is the void ratio, and for V volume of solids is equals to 1 meter cube. Your volume of voids is E meter cube. E meter cube this is actually E meter cube, and from that I can write your total volume is actually 1 plus E meter cube, 1 plus E, and volume of voids is actually E. So this is the equation, E by 1 plus E. That is the value of porosity. So let's substitute the value of E, 0.3245 divided by 1.3245. So that porosity is 24.5% when you multiply that 100. 24.5%. Okay. Let's go for the final problem of this lecture, final part of the final problem, we can say. Problem 9. Problem 9 of this lecture. Let's write that problem. The dry unit weight, the in situ, the on-site gamma dry of the sand, is 16 kilonewton per meter cube. And this sand this is used as subgrade for your road. So for road, we had 3-4 different layers of. If we have a road, what we call as, if we have a road construction, for that road pavement, we need 2-3 different layers. One is your base, one is your sub base, and one is your subgrade. 3 to 4 different layers we need, and one of the layers that we call as subgrade, and we have used sand for that. Okay. Now we are going to do one thing here. We are adding 5.5 kilonewton of dry sand and plus silt. So mixture of these two. So 5.5 kilonewton mixture of dry sand and silt is added, but this is dry. Both are dry. Actually, both are dry. I can write dry mixture of the sand and silt is added to this what you call as to 1 meter cube of subgrade, to 1 meter cube of this sand, initial dry that initial sand. So initially you had 1 meter cube. Let me show that perspective. You had initially 1 meter cube of subgrade, and this subgrade was entirely because of dry sand. This was your dry sand. Now we are having a mixture of dry sand plus silt, so that's 5.5 kilonewton. Okay, that we are adding to 1 meter cube of this subgrade. Okay, so we are adding some 5.5 kilonewton, some part of 5.5 kilonewton of this mixture to this 1 meter cube of the subgrade. Okay, after that, what's going to happen? Now it's saying that because of this, your volume is going to change by 1 times your final volume is actually initial volume times 1.2. So your volume got increased by 20%. Volume increased by 20%. So these are the 3 statements. Okay. Now we need to find the reduction in porosity achieved. Find reduction in porosity that we have achieved. Find the reduction in porosity that is achieved. Porosity is N. So we need to calculate what is the reduction in porosity because of this effect. So initially we have dry sand of some density, dry density is there, and we have used 1 meter cube of that subgrade. Now we are adding one more part, that is 5.5 kilonewton mixture of that dry sand plus silt, and because of this your volume is increasing by 20%. and calculate the reduction in porosity. And one more data is given to you that assume that G value for the solids of slit and sand are same. So that is G for the slit solids and sand solids is same, that is 2.67 for both the materials, 2.67. So let's go for the solution. Let's talk about the initial part. Let's talk about the initial part, that when there was only 1 meter cube, initial part of the problem. Let's talk about the initial part of the problem when there was only dry sand. This was only dry sand, and the volume was, how much was the volume? 1 meter cube was the volume. 1 meter cube was the volume, initial volume. Okay. And can you know what is the, based on the equation that gamma dry sand is 16 kilonewton per meter cube, what that means actually? If we talk about the first part, so if I say this is the solution, I would say gamma dry of the sand is 16 kilonewton per meter cube. What that actually means, that is weight of the dry soil divided by weight of the dry soil divided by total volume of the soil. That is actually weight of solids by volume of soil. Now, if the volume is actually 1 meter cube, if the volume is actually 1 meter cube, if the total volume is actually 1 meter cube, can you tell me what is the weight of solids for 1 meter cube based on the gamma? So if I say if I say that your volume is 1 meter cube, can you tell me what is the weight of solids? Is that 16 kilonewton? So your weight of solids initially is equals to 16 kilonewton. 16 kilonewton. 16 kilonewton. So this is the case 1. At that case, can you tell me what is the porosity initially at this stage? What was the initial porosity at this stage? Porosity. Can you calculate porosity at this stage? That is volume of voids by volume of total volume. And how can you calculate volume of voids? This is the concern. This is the concern here. How can you calculate volume of voids if you don't know what is the other things? So at the dry condition, for the first case, we are having a two-phase diagram. We are having two-phase diagram. We have a volume of voids and we have a volume of solids. We have volume of voids and we have volume of solids. If I get the volume of solids, somehow can you get the volume of voids? I would say yes. I would say yes. Your total volume is 1 meter cube. Your volume is actually total volume of 1 meter cube. Now we need to calculate somehow volume of voids. For that, we have to calculate volume of solids. So I would say that volume of solids is actually, volume of solids for the first case is actually G gamma W, weight of solids by G gamma W. And weight of solids we have 16 kilonewton. Your G value is 2.67 and your gamma W 9.81 kilonewton per meter cube. So that's your volume of soil. Volume of solids 0.6109 meter cube. And that means your porosity is actually, your porosity would be, that means your volume of voids is actually 1 minus volume of solids, that is actually 1 minus 0.6109 meter cube. So your volume of voids is coming out to be 0.3891 meter cube. And from that, I would say porosity would be N. Let's write it as N naught, initial condition of porosity, N naught. So your initial porosity would be 0.3891 meter cube divided by 1 meter cubes. That is actually 0.3891, or we can write 38.91%. This is the initial porosity we have. Initial porosity. Okay. Now we have the second case. We are adding how much? 5.5 kilonewton. Because of that, there is increase of volume by 20%. That means final volume is 1.2 meter cube. So let's have the final second case of that problem. Let's take the second case. So second part of the problem is there. Second part of the problem is there. Let me copy this part. Let me copy this part. So this is same. Now we are going to add one more part here. We're going to add one more part here. That is how much kgs we are adding? How much kilonewton? 5.5 kilonewton of that mixture, such that this volume is contributed equals to 0.2 meter cube. Can we say that? Such that final volume, let's write that in terms of final volume. Let's write in terms of final volume. So final volume is actually, final volume is equals to 1.2 meter cube. So this is our second part of the problem. Can we calculate what is the porosity at the second case? We would write it as N2. Let's write it as N2. Porosity in the second case, that is actually volume of voids in the second case divided by what we can say, total volume of the soil now. So total volume of the soil now is actually 1.2 meter cube. And can we calculate what is the volume of the voids in the second case? That's actually total volume. That's actually total volume minus volume of solids in the second case. VS2 we can write volume of solids in the second case. Volume of solids in the second case. How can you calculate the volume of solids in the second case? If the G value is same, so we are safe that I would say your calculations become easier. If the value of G is same for the silt and the sand, and you are adding 5.5 kilonewton, and can you calculate what is the volume of the sand, volume of the total sand? That's actually what is the total weight we have in the second case. Weight of the solids, that's actually 16 kilonewton plus 5.5 kilonewton. So total weight of the solid is for the second case is 21.5 kilonewton. So I would show here in the diagram that total weight is actually 21.5 kilonewton. And since for the second case G is same for both the materials, in this case we have dry sand, in this case also we have dry sand, but we have also silt. But G is same for both materials. That means your calculations become easier. So I would say your volume of solids for the second case is actually weight of solids in the second case divided by G gamma W. G gamma W. So we can substitute that 21.5 kilonewton by 2.67 into 9.81 kilonewton per meter cube. So that's your volume in the second case for your solids VS2. That comes to be equals to 0.8208 meter cube. So I got that 0.8208 meter cube. So I can solve for the porosity too. 0.8202. Then finally divide by 1.2 total volume. This is your void ratio. This is your porosity. And finally it's coming to be 31.60%, or we can write 0.3160, 31.60%. And can you tell me what is the reduction in porosity? That was the problem. What was that was the part of the problem we need to say. What is the reduction in porosity achieved? So that is the difference of N1 and N2. So porosity achieved, reduction in porosity I would write, decrease of porosity actually achieved is actually N2, or we can write N0 minus N2. What was the initial porosity we have? 38.91. 38.91 minus your second porosity, N2 31.60. So what is the difference? Is that 7.31? So this is the percentage of reduction. This is the percentage of reduction. Now coming back to the second part of the problem. Let's go for the second part of the problem. Second part of the problem is there. Now we are adding 1.5 kilonewton of clay, and clay is having a moisture content or water content is there. It's having moisture content of that 10%. Moisture content is there 10%. Okay, but because of addition, this we are going to add. This amount of clay we are going to add, but there is no change in volume. There is no change in volume. Change in volume. Okay, get further reduction in porosity. Get further reduction in porosity. Get the further reduction in porosity. So we need to calculate porosity N3. So now we need to calculate porosity N3. So it's saying that we are adding how much? 1.5 kilonewton of clay. But the clay is having some moisture content also. So there is moisture content also. So to make the phase diagram for this third case, I would say you are having some, initially you had that how much initially? 1 meter cube of that dry sand. After that you added how much? That 5.5 kilonewton. From the side we can show 5.5 kilonewton. 5.5 kilonewton of that mixture, and this was 16 kilonewton. Now in the third case you are adding what you call as 1.5 kilonewton of that clay, add the moisture content, some moisture content is there. So I would say initially this was all dry. Initially this was all dry. Now because of this moisture content, there is some water content also. There is some water also associated with here. I would say there is some water also. Let me show by different color. There is water also somewhere. Let's say there is little bit of water. Let's say this is some water also. Water. Let's say this is water. Water because of clay. Because of clay. And there we have some air left. Air is also left now. Final value of air is that is left. And because of this, what you call as clay, you are adding some weight of the clay also. We are adding some weight of the clay also. So there's some weight of the clay also. There's some weight of the clay also. So this is weight of clay. Weight of clay. Weight of the clay. And so final weight of the soil solids is actually, how much is the weight of the soil solids now? So weight of the solid is actually now 16 kilonewton because of initial value and 5.5 kilonewton because of the second condition. And because of the third condition, we are adding how much weight? We are adding 1.5 kilonewton. This is because of that's clay. That's having moisture content also. Moisture content. So we can get the dry weight also from the relations we know. Okay. Now, can you tell me what is the weight of the that clay solids? Can you calculate the weight of those clay solids based on the first derivation we have? Based on the first result we have derived, that first relation, weight of solid is equals to total weight of the soil specimen divided by 1 plus water content. This is the relation. So I would say for your 1.5 kilonewton of clay, you are having some water content of 10%. So this is your weight of solids of clay. This is your weight of solids of clay. Weight of solids of clay. So this much amount of weight of solids is for clay, 1.363 kilonewton. Okay. So why do I want this amount of clay? Why do I want this amount of weight of solids? What is the need of this? It's saying that volume is not going to change. So if the volume is not going to change, initially you had volume of 1.2 meter cube. Volume is not going to change. That means your clay, this weight of the solids would occupy some space. It would occupy some volume of Vs of the clay. So because of that, it is going to go occupy the voids we have. The void is left, which we're having in the second case, that the voids, some of the voids are going to be replaced by that volume of solids of the clay, because volume is not going to change and solids are incompressible, so though they are also not going anywhere. So your volume, that void ratio is going to be changed. If your void ratio is going to be now changed, so porosity is going to be changed. So this, we need to say how much volume these solids of clay are going to be occupying. So for that, I would say, what is the specific gravity of those clay solids? G for the clay solids. What is the value of that? Is that given? That is given to you 2.55. So the specific gravity of clay solids is 2.55, and I need to say what is the volume of the clay solids? A volume of solids of clay. That is actually weight of solids of clay divided by G of the clay into gamma W. So this much amount of water volume is occupied by those solids of clay. That is some value in the range of 0.0545 meter cube. So this much amount of total volume of the solids that's occupied by the total volume that was left for the voids. Now it has occupied by that solids. So I would say the porosity 3, now the final porosity N3 can be calculated by volume of voids for the third stage divided by total volume of the soil. Total volume of the soil. Total volume of the soil is going to remain fixed, 1.2 meter cube, and volume of soil, volume of what you call as volume of voids in the third case is actually total volume of solids, total volume of soil minus volume of solids in the initial case. In the second case, that we can write Vs2. In this case, Vs2, where we had that calculations. So this Vs2, we had that Vs2 here. This Vs2 is this is not going anywhere because solids are incompressible. So Vs2 is there. So Vs2 we can write. This is Vs2. After that, we have to subtract the volume occupied by the clay solids. Volume occupied by clay solids. That is 0.0 0.0545. So 0.0545 meter cube, we can write there. This is the volume of solids of clay, and this was your VS2 equals to, we have already calculated that, 0.8208, 0.8208 meter cube. And finally, your third porosity, final porosity, is actually N3, that's 26.98%. So finally, I would say further reduction in porosity is actually difference of N3 and N2. Reduction in porosity, that is N2 minus N3. N2 value, what is the N2? N2 is 31.60, 31.60. So that is 31.60 minus 26.98. How much percent reduction is further in the porosity? 4%, 4.62%. So this is the final solution. This is the final solution. I hope you enjoyed that problem. Thank you for watching that. Those problems related to that soil properties. I would say thank you for watching these.